Hello, everyone, and welcome back to another planetarium show. My name is Jessica. I'm the director of the planetarium, and with me tonight are two of our student workers, and I will let them say hi and introduce themselves, and we'll start with Miss Rachel.
Hi, I'm Rachel. I'm a sophomore here at UMD, and I'm studying biology and environmental science.
Hi everyone, I'm Luis. I'm a senior here and I'm studying chemical engineering.
Awesome. So we have a very fun show for you tonight that we haven't done in a while, and that is Adventure Through the Universe, where we're going to attempt to see as much of the universe as we can in about 30 minutes. Um, it's a wild ride. But before we get started, as always, if you have any questions throughout the show, feel free to leave them down in the comments. Louise will be keeping an eye on that for me. Will let me know if questions come up. We'll also have time for questions at the end, as usual. And I'm going to try out using polls tonight to kind of have you guys guide us on some of the things that we go and see. Speaking of which, let me go ahead and get the first poll going. There we go. Okay, first poll is up because as we get started, we're going to start off in our own solar system. And since we don't want to do an entire just solar system show, because we have a whole show for that, I only want to go visit a couple of the planets. So I'm going to let everyone in our audience pick. You can decide which inner planet we're going to go see. And then after we go visit that, we'll pick which outer planet we want to go see. So go ahead and get your votes in as I get everything up and running, which shouldn't take too long. And myself. All right. So, as I said, we are starting off our adventure through the universe looking down at, well, at least where we are. At the planetarium, we're looking down at the planetarium on UMD campus, but we'll just go ahead and launch up into space. And get a view of our beautiful Earth out in space. Then we're going to swing around and kind of look down at our solar system. Because, of course, Earth isn't the only planet there. We have the sun sitting at the center of our solar system. We have 8 planets. We have asteroids and comets and all sorts of stuff. So we're going to go visit a few of those items today. And like I said, we're going to start with one of the 4 inner planets, and that's Mercury, Venus, Earth, or Mars. And I'm not seeing any votes come in. I don't know if just no one is voting or if maybe it's glitching on my side.
We do have a comment on where we should visit from Kathy.
That would
We
be my
have
mother.
Mars and Pluto.
Okay, well, Pluto doesn't count yet, but I will go see Pluto, Mom. She knows me. All right, well, since that's the only vote I'm seeing for a terrestrial, let's do Mars. Let me stop the poll. Okay, awesome. All right. And we will go see Mars. This is me attempting to do way too many things at once. All right. Oh, hi, Danielle. Just got like my family watching. Okay. So swinging into Mars here, conveniently known as the red planet because it looks red. And that red color actually comes from rust, iron oxide, which is just covering the surface, the rocks, the soil, all of that, and that gives it that orangish, reddish tinge to it that rust has, which is pretty cool. Mars is actually a fairly small planet. It's half the size of Earth. And that's shocking to a lot of people because of our fascination with Mars and all the stuff that we have going on. I think a lot of people assume that Mars is the same size as Earth, but it is about half the size of Earth. But despite that, it has some really interesting features. And it doesn't look like any of them are in the daylight right now. So I'm just going to use a little bit of planetary magic here. We're going to speed up time. And we're going to go see first this big canyon system. So this canyon system is called Valles Marineris. It is the largest canyon, not just on Mars, but kind of in the solar system. It's a lot like our Grand Canyon, but much grander. If this canyon system was on the Earth, it would stretch across the entire United States. And it's on average 3 to 4 times deeper than our Grand Canyon. And given the size of Mars, this canyon stretches over about a fifth of the circumference of Mars. So quite a big canyon. And we're still trying to understand what formed it. I mean, we know that there was liquid water about 3 billion years ago on Mars, and that would have led to erosion, which of course created the canyon systems that we have on Earth, and that would have contributed. But because the water wasn't around for as long on Mars, we're not quite sure how this canyon got as big as it did, if it was just erosion. So there's some thought that there might be some like small scale plate tectonics, where at this particular point in Mars, the crust just kind of pulled apart and started this rift, and then erosion just made it bigger and deeper. But there's still a lot that we're trying to better understand about all of that. All right, and then the other really cool feature to point out is right here. This is a volcano, Olympus Mons, which is the largest volcano on Mars and the largest volcano in the solar system. This volcano is so big that it would cover the entire state of Arizona, and it's about 3 times taller than Mount Everest. Now, this isn't an active volcano anymore. At least we don't think so. We haven't seen any evidence of active volcanic eruptions on Mars. But we know that there had to be a lot of activity in the past in order to build up a volcano of this size. And it's not the only one. We do have other volcanoes as well. Let me try and do another poll real quick to see where we want to go to next as I finish up talking about Mars. And as we pull back away from Mars, we can also see that it has 2 moons. They are Phobos and Deimos. And if we go take a look at one, we see that both Phobos and Deimos, we're looking at Phobos, but Deimos looks pretty similar, would be what I lovingly call a lumpy space potato, just a chunk of rock. And because of its appearance and it's made of rock, we actually think that both Phobos and Deimos are captured asteroids, since Mars sits on the edge of the asteroid belt, which, as we fly back out from Mars, we can try and see. It's been a while since I've used this program, so I'm a little rusty. All right, I'm not seeing it, but the asteroid belt lies in between Mars and Jupiter. All right, well, now it's time to go adventure to one more planet. We're going to go look at one of the 4 outer planets. So that's Jupiter, Saturn, Uranus, or Neptune. I am seeing a vote for Saturn, and I think there was a vote in the comments for Saturn as well. So that is what we're going to go see. Very good choice, a very popular choice. So let's fly on in. and take a look at the second largest planet in our solar system, which is Saturn. Now, as we fly in, you can see a lot of moons around Saturn. Saturn currently has 82 moons, which is the most of any planet in our solar system, at least of what we've found so far. Jupiter is a close second with 80 moons. Saturn has 82 moons. Most of them are lumpy space potatoes, like Mars's Phobos and Deimos. They're captured asteroids or comets. But there are some others that are really cool, which we'll go see in a minute. But we are here at Saturn, as I said, second largest planet in the solar system. Absolutely beautiful. We have these really pretty stripes in the clouds. And these are cloud patterns that are kind of rising and falling. So one stripe is like rising clouds, and then the next stripe would be sinking clouds. In general, we think the lighter colored stripes are rising, and the darker colored are sinking. But they are very beautiful. And then, of course, what Saturn is most known for are its rings. These rings, even though they look to be solid, are not. They are made up of millions and millions of pieces of mostly ice. There's a little bit of rock mixed in there, but it's mostly ice. And this ice ranges in size from about the same size as a grain of sand, all the way up to chunks of ice the size of a house. Most of them are on the smaller end, though. And that's why the rings are so bright and easy to see, is because they're made up of a lot of very reflective ices. They reflect a lot of light, and so they're easy for us to see. And in fact, we don't think Saturn's rings are always this big and bright and magnificent. We think what we're seeing is a temporary enhancement that's happened in the past probably 500 million years. What we think is a comet got a little too close to Saturn, and Saturn's gravity ripped the comet to pieces. And now all of those pieces are currently orbiting around Saturn in its rings, and that just gave a sudden just lot of material to the rings, which made them a lot bigger and brighter and better than they would be on the average. So we seem to be in a fortunate time where we're seeing this temporary enhancement to Saturn's rings. Now, I mentioned lots of moons, and we're going to go see one moon, because, again, we have an entire show about moons in the solar system. But the one I want to show you, let me find it in my list here, is Saturn's largest moon, which is Titan. Well, Titan is Saturn's largest moon. It's also the second largest moon in the solar system. The largest is Ganymede, which is one of Jupiter's moons. Titan is so big that it's actually bigger than the planet Mercury and a little more than half the size of the planet Mars. And it is very unique for a moon. Titan actually has an atmosphere, which we don't see on any other moon. And it's a thick atmosphere. It's actually about 1.5 times the thickness of Earth's. And that in and of itself makes it extraordinary. But it also has lakes of liquid on its surface. And we can see them, let me spin us around here, right around here. They're mostly found around the North and South Pole. Now, I said lakes of liquid. I didn't specify what the liquid was. We would immediately assume water, but that's not the case. We are so far away from the sun, it's way too cold out here. You're not going to have liquid water, at least not on the surface. These are actually lakes of liquid methane. And we think that Titan has the full precipitation cycle that we have here on Earth with water, but just with methane. So we have methane clouds, it rains methane, methane collects into lakes and rivers, and we see evidence of rivers that have since dried up, but we see those meandering kind of dried up riverbeds. So it's a really just similar, but also very different environment than what we have here on Earth. And we're particularly interested in learning more about it because while life as we know it depends on liquid water, there's not to say you couldn't end up having a form of life that depends on liquid methane instead of liquid water. So we're very interested in learning more about this unique moon, seeing the possibilities of some never before thought of type of life. And we are actually in the works of sending a new mission to this moon. Its name is Dragonfly. It's a little quadcopter. Because there's a thick atmosphere, so you can fly through it. So this little quadcopter is going to fly around Titan and take a lot of information, at least until it probably freezes, because it's very cold out here. All right. So I think that's a good quick look at a few things in our solar system. And we'll turn ourselves around, orient ourselves with the sun again as we move out and away from our solar system. Okay. Trying to find something real quick. Not seeing it. Why am I not seeing it? Anyway, okay. Let's get back to the show. So, as we fly away from the Earth, we see, of course, that our sun is just one of many, many stars out here. And as we move away, it takes a while, but we finally do end up in the realm of the stars. So the closest star to us sits about 3 light years from Earth. What that means is it would take you 4.3 years traveling at the speed of light to reach this star. Now, we can't travel at light speed, so traveling at the speed of the fastest known spacecraft, it would still take us, I believe it's on the order of like 10,000 years to get to the closest star to us. And most stars are much further away than that. So currently, traveling to other stars doesn't really seem to be in the realm of possibility. But one of the reasons we'd be interested in doing that is as we've been looking at the other stars, we have found so many of them actually house planets. So every star that you're seeing here that's circled in blue, that is a planet, or that is a star that we have found at least one planet around. Based off of our current studies, we estimate that at least half of all stars in our galaxy have planets. And at, a couple 100 billion stars in our galaxy, that's a lot of planets. But more than that, we actually think about 20% of those is likely to be an Earth-like planet. Which again, 20% of a couple 100 billion, that's a lot of possible Earths out there, which means we're probably not as unique as we originally thought, which I personally don't think is a bad thing, but I think everyone will have their own kind of opinions on that. All right. So as we're out among the stars, I think the next good thing to go look at would be some groups of stars, because most stars are actually not alone. Most stars are born in groups of lots of stars. And depending on the exact size of that group, we have different names for them. So the first thing we're going to look at are what we call open star clusters, and they're highlighted in green. And the best example of an open star cluster is the Pleiades. So this is something you can see actually up in the sky now during the winter. So an open star cluster tends to have fewer stars. We're talking like tens to hundreds of stars that are more spread out. They're not like super close packed in together or anything. And they tend to be much younger populations of stars. And that's because these stars don't stay in this group, don't stay in this open cluster. Because as they pass by other stars, gravitational pulls from other stars is going to pull this group apart. And so they don't stick together forever, which is why we see them mostly as young star systems, because older stars would have been pulled apart from their group. Now, the other type of star cluster that we can have is a globular cluster. And those look a bit like this. This is M13, I believe this one is the Great Globular Cluster of Hercules. And you can see it looks a good bit different. One, there's a lot more stars. We're talking thousands to tens of thousands of stars in a globular cluster. We also see that it's roughly spherical in shape and very densely packed. The stars are very close together. And the globular clusters tend to be much older populations of stars. In fact, the oldest stars in our galaxy are in globular clusters. So these seem to be groups of stars that were among the first sets of stars to form in our galaxy about 13 or so billion years ago. All right, now in addition to stars, as we fly on out, we're getting a really good view of our Milky Way there. And you can see all of that kind of brown and dark fuzziness. Those are clouds of gas and dust, which is all throughout our galaxy. And we call these clouds of gas and dust nebulae. And there are several different types of nebulae. The first is, here we go, we call it an H2 region, or a star-forming region. And a great example is the Orion Nebula, which is in the constellation of Orion. It's the central point in his sword. And these are giant clouds of gas that are actively forming new stars. So those open young star clusters formed in a star-forming region in a nebula like this. So we're seeing, hundreds of stars forming in these gas clouds, so that kind of hopefully give you an idea of how big, truly gigantic this cloud of gas and dust is. And we see all of these kind of swirls in the gas from all of the young stars kind of pushing the gas around. We see different colors based off of the colors of the stars, and also the gas itself is being heated by the stars and also glows. And so we're seeing all of these really pretty structures and colors within the star-forming regions. Now, the other two types of nebulae, instead of being associated with the birth of stars, they're associated with the death of stars. So the first one we're going to look at are planetary nebulae. And a great example is the Ring Nebula here. So planetary nebulae is what results after a small star, so a star like our sun, after it dies. What happens when a small star reaches the end of its life? It's running out of hydrogen to fuse into helium in its core. And so as it's running out of fuel, the outer layers start to puff out, and the star gets bigger and bigger. And it goes through lots of complicated things. In fact, I talk about this. We did a whole show, I believe a couple months ago, on the life cycle of stars, so you can go and find out more there. But what ends up happening is it puffs up so big that it actually loses hold of those outer layers, and those outer layers slowly kind of float away. And over time, you have most of the star expand out and then float away. And at the end, you're left with just the dead core of the star, which we call a white dwarf, surrounded by all of this really hot gas that was once a part of the star and now has floated away. And so this is what we call a planetary nebulae. And this is, again, what's going to happen to our sun. Now, for stars that are very big, the most massive of stars, they have a much more violent death and end up going supernova and end up as supernova remnants. And so what ends up happening is the star itself explodes, and that, of course, ejects out most of the gas that was part of the star, leaving behind either a neutron star or a black hole. And then that is surrounded by all of this hot gas that was exploded out during the supernova, and that remnant of gas is what we call a supernova remnant. And you can see, so this is the Crab Nebula. You can see that it has a lot more complexity in its structure, because instead of being a very gentle, just kind of like puffing out of the outer layers of the star, this was a chaotic explosion. And you see that in the overall structure of the supernova remnant. All right. So let's keep flying on out from our galaxy here. And we're going to take a look at our galaxy, the Milky Way, or at least what we think it looks like, right? Since we're inside of the Milky Way, it's hard for us to know exactly what it looks like. But we think that our Milky Way is a spiral galaxy, and we live about halfway between the center and the edge. And what I'm going to do real quick is actually turn on Constellation Lines. So these are the lines that connect the stars that we see in our sky to make the constellations. And you notice all of them are concentrated in a pretty small, thank you, train. I don't know if you guys can hear that. Anyway, they're concentrated in a very small portion of our galaxy. That's highlighting really the stars that we see in our nighttime sky. We really only see the closest couple thousand stars in our galaxy, and that's it. Most of our galaxy is too far away for us to see in our nighttime sky. We just see that fuzzy haze of the Milky Way, and that's everything else that exists that's too far away to see as like individual stars and objects. But our Milky Way is not alone. We are not the only galaxy out there. In fact, we are a part of what's known as the local group. You can see the kind of green spots are highlighting our local group here. So this is a group of about 60 to 70 galaxies. Most of them are very small, what we call dwarf galaxies, but there are 3 large galaxies in our group. We're actually the second biggest. The biggest galaxy is the Andromeda galaxy, then the Milky Way, and then the third is the Triangulum galaxy. But as we fly away from our local group, we start to see more and more galaxies out there. So every point of light you're seeing is another galaxy. All of the different colors are related to the different surveys that were done that found all of the different galaxies that we're seeing. And of course, as we continue to go out, we see more. And more. Let me go back in just a little bit more before the CMB turned on. So yeah, again, every single point of light that you're seeing is another galaxy. There is an estimated 2 trillion galaxies in our observable universe. Now, you may also notice that the way I have it oriented right now, there's kind of a wedge at the top and a wedge at the bottom that doesn't have any galaxies in it. It's not because there isn't anything there. What's happening is to see in those directions, we have to look through our own galaxy, which is filled with stuff. And so it blocks our view of anything else that's outside of it. So it's just, we can't see in those directions because our galaxy is blocking our view. But based off of what we see everywhere else, we fully expect that it's going to look just like everywhere else and be just as full of galaxies. And then if we keep going out, we reach the edge of our observable universe. Now, this isn't necessarily the end of the universe itself. It's just the end of what we can see of the universe. And this happens because of two reasons. One, light has a speed. It's not instantaneous. It takes time to travel from one point to another. Second reason is our universe has a finite age. It's about 14 billion years old. And that means that light has only had 14 billion years to travel from an object to us. So if something, say, lives 15 billion light years away, it's there. There just hasn't been enough time for that light to reach us. So there's a limit to what we can see today based off of that. So each second, as our universe gets older and older, those limits expand and our observable universe grows, and we will see more and more of our universe. So this is just what we can see right now. All right, and with that, we are going to make our way back home, flying through the galaxies, finally making it back to our galaxy. Where we will fly through the stars of our galaxy until we reach our sun. And let me target it. Till we are finally back to our home planet of Earth. And with that, we will end our adventure through the universe, seeing quite a good bit. But of course, there is even more out there that we have not gotten to. But that would take quite a long time, and we generally don't like to do shows that long. So that concludes our adventure through the universe, and let's see if we have any questions. Right, there we go. No
I don't
questions.
see any new. Yeah, I don't see any new questions. So.
All right, well, now is a great time. If you have any questions, you can leave them down in the comments. We'll stick around for a few more minutes to see if any questions do come in. And let's see. I was going to say something, and I completely forgot what I was going to say. I forgot what I was going to say.
It
Okay,
happens.
it does.
Definitely happens.
It's been a long day. All right. So while we wait for more questions to see if there are any questions that come in, I can go ahead and tell you what's coming up over the next week. So on Wednesday, we are going to do another edition of Ask an Astronomer, where we will be here to answer your questions, whatever questions you may have. We're here to answer them, hopefully answer them. I don't know, we'll see if we get stumped. I don't think it's happened yet. And then next Saturday is the next edition of our exploration series, where we're actually going to take a up close and kind of deep dive look into these nebulae that you kind of had a little introduction to tonight. So we're going to go into a lot more detail about those. And then that's going to be the last of our shows for 2021. After exploring nebulae, we are going to take a couple weeks off for the holiday season, but then we will be back in January with What's Up January and January constellations, and be back to our regular schedule again. And possibly opening up the planetarium. Fingers crossed. We gotta see how things go.
Be very fun.
I think all of us would love to finally be able to open first, at least a few public shows. I don't think we're going to be able to answer or open up for our full schedule yet, but at least to be able to do a little bit would be nice. Especially since we got our fancy new system, and I don't know that I've said this on a stream, but our audio system died about a month ago. So that's been part of the delay, is we're getting new equipment for our audio, and that should hopefully all be fixed by January. So fingers crossed. We'll see how things go. But I know we're very excited to be able to open again, and also just want to show off the new system. Like, we've got some really cool things that we can do with it that, like, we've never been able to do before, and I'm very excited to get people in there. All right. Let's see. Oh no, I'm sorry, Danielle. It's okay. It's okay. I will help you get over it. I'll just, immerse you in my shows more. All right, I think we will end there. Thank you everyone so much for joining us. Have a wonderful rest of your weekend, and we will see you next time. Bye, everyone.